Hey guys, this is Professor Janacek, and I want to talk to you about Green's theorem. This is a very exciting theorem. To begin with, we'll let C be a simple, closed, piecewise, smooth curve. Make sure you understand what that means. And it's oriented counterclockwise, that's positively. And we'll let R be the simply connected region that's enclosed by C. So C is a curve that's on the boundary of our region R. We'll also go ahead and let F, we'll define F as the force with the components F and G. All right, there are two forms to this theorem. The first one we call the circulation form, or as sometimes referred to as the curl form or the tangential form. Let's talk about what that looks like. We have the line integral of f dot dr, which by the way is the same as the line integral, this is over our curve C, of f dx plus g dy. On the right side, we have a double integral over the region R of the partial of g with respect to x minus the partial of f with respect to y, and this integral is being taken with respect to the area of our region. Let me go ahead and make note of what the flux form is, and then we'll talk about these two forms. So the flux form, also known as the divergence form or the normal form, here we have the line integral, again, over our path, our curve C, of f dotted with n ds. Now, what is that n? N is the normal, the outward unit normal vector on C. So it's unit normal vector along that boundary C in the outward direction. By the way, that line integral can also be written as the line integral, again, over C of f dy minus g dx. Notice there is a distinction to the circulation form. Now, on the right-hand side of this, we have, again, a double integral over our region R of the partial with respect to f of with the partial of f with respect to x minus the partial of g with respect to y, and that double integral is being taken, again, with respect to the area of our region. So let's talk about these just a bit. What makes this so very powerful is that we can actually write these integrals in one of two ways. We can find this information one of two ways. We can set up a line integral. Notice this is a line integral. As is this, we've got our line integral. So sometimes those are really easy to work. Sometimes they're not. If they're easy, we go with the line integral. If they're not, we have this option of looking at a double integral. Again, sometimes those double integrals are really easy, sometimes they are not, but this is really great because I have options. I can either look at the double integral. If that's easy to work, I'll go with that, or I can use the line integral if that's easy to work. If that's the easier one, we'll go with that. So it's really, really quite nice. I want to mention a couple other things. These pieces in here have special names on those double integrals. In the circulation form, this value right here is called the two-dimensional curl. And that's where it gets the name, the curl form. Whereas in the flux form, as you might guess, this is referred to as two-dimensional flux. All right, so let's go ahead and try an example and see if we can kind of figure out how this all works. Let's let F be the vector field, -3y and 3x, and we'll let our region R be the triangle with the vertices 0, 0, 1, 0, and 0, 2. So what do we do? Well, first, I'm going to let lowercase f be negative 3y and lowercase g be 3x. And then we want to come up with our paths. So let's take a look at the line segments. So again, what we're looking at is basically finding the piecewise smooth curve C. How can we describe that? So let's go from 0, 0 to 1, 0. Now you'll have to remember how to find equations of lines or line segments. So we're going to have that restriction, that parameter t pop up here. So I'll go ahead and use the notation R01. Since I'm going to have to do this 3 times, I won't just call it R0, call it R01. That is the vector 0, 0. And then V1, remember how we find that? That is 1 minus 0, 0 minus 0, which gives us the vector 1, 0. And let's see, remember this is for our parameter t going between 0 and 1, this situation, that's what we can use. Then R1 would give us t0. Again, please review how to find equations of lines or perhaps line segments. It's more appropriate. Now I'm going to need that, but notice looking at the line integral, I'm going to need dr here. So let's go ahead and find that as we go through this. So R1 prime is 1, 0. And now let's also figure out, well, what is f evaluated at R1? So remember what f is. Here's f evaluated at R1. What do we get there? Let's see, that would give us 0 for y. That's going to give us 0, 3t. All right, that's the first piece. Now let's look at the segment that goes from 1, 0 to 0, 2. Go through the exact same process. R0, 2 is the vector 0, 1, 0. And then V1 is 0 minus 1, comma 2 minus 0, which gives us the vector negative 1, 2. And so R2, remember using the same parameters, t goes from 0 to 1. R2 is 1 minus t. Just again, make sure you remember how to find this r. There's a formula for that. And let's see, so 1 minus t, comma, that would give us what, 2t. Again, finding equations of lines. So let's see, that would then give us an R2 prime. Again, I'm going to need that in my circulation form. That would give us what, negative 1, 2 for R prime. All right, so now going back to just R2, what is f of R2? Again, looking at R2, evaluating f at R2. What do we get there? Let's see, that's going to give us negative 6t and 3 minus 3t. All right, so there's f evaluated at R2, and again, that we're going to need that. So these bits here will be f And this, oh no, r primes will be used for dr. But we have one more. This is a triangle, by the way. So we have one more line segment to come up with, and that's the segment that goes from 0 to 0, 0. All right, so we'll call this R0, 3. Our first vector is 0, 2. And then V3, remember how to find that. That's going to be 0, 0. I'm sorry, 0 minus 0, and then 0 minus 2, which gives us the vector 0, negative 2. So R3, again, that comes from our formula that we learned previously. That is going to be, let's see, the vector 0. Oh, and that'll be 2 minus 2t. All right, so that will allow us to find R3 prime, which is 0, negative 2. And then also f of R3, again, putting R3 into f, R3 into f, noticing what are we going to use for x, what are we going to use for y. So that will give us the vector field, oh, that's what, negative 6, comma, oh, wait, no, there's more to it. I'm looking at R3 here. Negative 6 minus 6t, and then 0. All right, so hopefully that's a bit of a review. I know there's a lot going on. The only real kind of thing that we haven't done a lot of before is evaluating this f, right? Evaluating those. But again, it's just putting R1, R2, R3 into our function f. Making sure you remember what's being used for x and what's being used for y. All right, I think we have everything we need. Now we are going to use the circulation form of this. Let's start with that. We're looking at the line integral over C of f dotted with dr. So that's going to give us the integral from 0 to 1. Again, that's 0 to 1 is our parameter t of f 0, 3t dotted with r prime dr, that's 1, 0. So notice, and this is integrating with respect to t. Notice all I'm doing is taking f times r, dr. Oh, not dr. There it is. So f evaluated at r1 dotted with r1 prime. We'll do the same thing for the others. So then we'll add to that the integral. Again, my parameter t still goes from 0 to 1 of f evaluated at r2 dotted with r2 prime. And then we have the last one, integral from 0 to 1. Again, that's my parameter t. And f in this region is negative 6t, comma 0. Oh, I'm sorry, negative 6 minus 6t, yeah, there it is, comma 0, dotted with r prime in this region is 0, negative 2, and we're going to integrate with respect to t. All right, so what do we get with all of this? Well, I can put them all together. It's the integral from 0 to 1. Take your time with these dot products. Hopefully you're pretty good at that now. we end up with, let's see, the first one is 0. The second one is -6. Oh no, that's +6. +6. And the third one is also a 0. Let's see, did I do that middle one right? Yeah, okay, I'm happy with that. And then we integrate that. Of course, that's just the integral from 0 to 1 of 6 dt, which gives us 6t evaluated from 0 to 1, which is just a 6. So there we go. So that is using the line integral. Okay, let's also take a look at this using the double integral. So notice for the double integral, again, we've got f is equal to -3y and g is equal to +3x. And so we'll need the partial of f with respect to x, which is -3, and the partial of g with wait a second, I said that wrong. It's the partial of f with respect to y, which is still -3. All right, that works. The partial of g with respect to x. Oh, that's actually +3. Okay, there we go. All right, so again, I'm looking at using this double integral here. We're still in the circulation form. Partial of g with respect to x minus the partial of f with respect to y. All right, so I think we're ready to set up our integral. So notice this is equal to the line integral, but I'm going to write out the double integral. Let's just jot it down so you know what that looks like. Gee whiz. All right, so this is what I'm actually going to compute. So let's see, that is the integral. Oh, let's see, we've got, I know it's going to be 3 minus -3, and then we'll go ahead and integrate, with respect to x and then with respect to y. So let's see, y goes from 0 to 1, x goes from 0 to 1 as well. So what does that give us? It's the double integral, both from 0 to 1. Let's see if I can clean that up. Integral from 0 to 1, integral from 0 to 1 of 6 dx dy. Oh, well, this is going to be an easy integral to work with. That gives us, again, the integral from 0 to 1 of 6x evaluated from 0 to 1. And that's going to be integrated with respect to y. That gives us, what is that? 6 minus 0, which is just 6 dy, which gives us 6y, evaluated from 0 to 1, which is 6 minus 0 as well. And look at that, it also gives us 6. Ha, how fantastic is that? All right, so the idea is that Either way, I should get the same thing. And again, that's the beauty of this, the power of this. I now have options. I don't have to just use a double integral, and I don't have to just use a line integral. I can pick between them. And so this is really great. If I have a line integral, I can look at it in terms of a double integral. Or if I have a double integral, I can look at it in terms of a line integral. Now, I want to talk about kind of the big picture. What is this saying? I know it has something to do with circulation and it has something to do with flux, but what in the world does that mean? So let's just talk about interpreting this. This basically tells me, and it's in either form, you can kind of get the idea. But what is the circulation form telling me? It's stating that the net rotation through the region, so if I'm looking at rotation within my region R, that equals the circulation just on the boundary of R. That's my curve C. So again, the rotation throughout R is equal to just the circulation on the boundary, just on that line integral. In terms of the flux, which we didn't do an example, but it's just as straightforward, dealing with the flux, it's going to relate the flux across the boundary. The flux across the boundary, that's actually this portion of it. So just the flux along that boundary C, it gets related to a property of the vector field within that region that produces the flux. So this is actually giving us the vector field, a property of the vector field that produces that region. So again, the flux within my region, I can now write that in terms of looking at just the flux on the boundary of that. So it's, again, extremely powerful. Instead of looking at the whole region, I can now just look at what's going on in the boundary, or I can go the other way. If I want to know what's going on at the boundary, I can look deeper into that region to get that information. This is very similar in concept to the fundamental theorem of calculus. So again, very, very powerful. Well, that's it for now. Enjoy.